In this video tutorial, we will talk about the different types of chemical bonds. So, why chemical bonds? If you recall, noble gases are the most stable elements on the periodic table. What do they all have in common? A full valence shell. As such, an atom tends to gain or lose electrons to become isoelectronic with the noble gas it is closest to. So isoelectronic means the same electron configuration, so the same electron pattern as the noble gas it is closest to. Take a look at fluorine. When fluorine gains an electron, it now has 8 valence electrons, and it is isoelectronic with neon, which also has 8 valence electrons. This is why nonmetals generally increase in reactivity as you go up the periodic table, while metals tend to become more reactive as you go down the periodic table. Generally, the nonmetals will want to gain electrons to achieve that full octet structure and become isoelectronic with the noble gas they're closest to, thereby giving them stability. The smaller the atom is, the easier it is for its nucleus to latch on and grab electrons, while bigger atoms, because the electron is so far away from the nucleus, it's hard for them to grab it on. So that's why nonmetals tend to be more reactive the smaller they are. And the opposite true is for metals. Metals want to lose electrons. But when the electron is so close to the nucleus can really hold tightly onto that electron. It's hard for it to be removed. Meanwhile, electrons that are far away from the nucleus can't really hold on tightly to them. It's much easier for them to remove, and thus metals tend to be more reactive the bigger they are. Now, how an atom gains or loses electrons determines the type of chemical bond that is going to be formed. This in turn imparts the substance with special physical properties. Now, throughout the unit, I will be using the phrase form follows function, meaning the form, the structure of the molecule will determine its chemical properties, its physical properties, its function. Now, if you recall, ionic bonds typically occur between an atom with a weak attraction for electrons, so it has a low electronegativity. Typically they are metals, and another atom with a strong attraction for electrons, so it's high En value, and those are typically going to be nonmetals. So looking at lithium, we see that it has an En value of 1.0, while fluorine has an En value of 4.0. So lithium has a very weak attraction for the electron, while fluorine has a very high attraction for the electron. As such, lithium will donate its electron to the fluorine, and in the process become a positive cation, while fluorine becomes a negative anion. You will now notice that both fluorine and lithium have a full outer valence shell, and they are now isoelectronic with the noble gas they are closest to. So lithium would be isoelectronic to helium because it has one shell that's full, while fluorine would be isoelectronic with neon because it has 2 shells that are full. You will notice that we place square brackets around both of them with an ionic charge in the top right hand corner to show that they are both ions. They are no longer the original neutral atoms, but charged ions that are stable. Please also note that I've written the ionic charges as 1 plus and 1 minus, not plus 1 or minus 1. By putting the charge at the front, that is referring to the oxidation number, which is something totally different than the ionic charge. We'll talk more about oxidation numbers when we get to the electrochemistry unit. Now that these ions are stable, they don't need each other anymore. So lithium has already given away its electron to fluorine. It doesn't need to be next to fluorine anymore. So why are they still bonded together? Because opposite charges attract. Due to their electrostatic attractions, the positive charge and the negative charge causes the lithium and the fluorine to attract one another. This is known as an ionic bond because it's a bond that's formed between 2 oppositely charged ions. So with ionic bonds, electrons are transferred from one atom to another. But what if electrons are shared between atoms? This typically occurs between atoms with a strong or similar attraction for bonding pair electrons, so if they have a high electronegativity value. So typically this occurs between nonmetals and nonmetals as they have very high En values in comparison to metals. Since only one pair of electrons is involved in this bond, we call it a single bond. Over here we see 2 pairs of electrons, so we call it a double bond. And over here it's a triple bond because there are 3 pairs of electrons involved. Now these pair of electrons are referred to as bonding pair electrons because they're involved in the chemical bond. Since these ones are not involved with chemical bonds, they're by themselves, we call them lone pair electrons instead. Now in this type of chemical bond, neither atom gets to permanently keep the electrons. Instead, they're going to share them equally. And so half the time, the electrons will spend their time around this chlorine atom, orbiting it. Then they'll spend the other half the time orbiting this chlorine atom. And they'll just go back and forth, orbiting both atoms. Now, if I go to a casino and I win $1, but then I lose $1, Am I richer or am I poorer? The answer is neither. I have broken even, which actually is a good thing. But similarly, when it comes to atoms, if you're losing electrons half the time, but then gaining electrons the other half the time, you're neither positive nor are you negative. Instead, you're going to be neutral overall because there's no net change in the number of electrons that is given to you or lost by you. And so molecules formed with non-polar covalent bonds tend to have very strong intramolecular forces, so that's the one that's holding the molecule together, but very weak intermolecular forces, so that's what is attracting two separate molecules. So just keep in mind, when we say intramolecular, we are referring to the force that holds the actual molecule itself together. Right? So the intra, within the molecule itself. On the other hand, an intermolecular force is what holds two separate molecules together. All right, so intra keeps the molecule itself held together. Inter holds two separate molecules together. So thus far, we have seen completely opposite ends of the spectrum. What happens when electrons are completely transferred, resulting in positive and negative charges, and what happens when electrons are equally shared, resulting in neutral and neutral charges. But what happens when the electrons are unequally shared between atoms? So polar covalent bonds occur typically when two atoms have a strong but unequal attraction for bonding pair electrons. So looking at oxygen, we see that it has an En value of 3.5, while hydrogen has an En value of 2.1. This unequal sharing of electrons results in the formation of partial charges. So we use this lowercase d, Greek letters, for slight, or partial. So slightly positive or partially positive, and slightly negative or partially negative. In such bonds, electrons will orbit the atom with the greater attraction more often, providing it with a partial negative charge. So in this case, the oxygen, because it has a higher En value, will take the electrons, and the electrons will spend most of its time around the oxygen, and every now and then go back to the hydrogen. So the oxygen is not strong enough to completely transfer and rip the electrons off and keep it around itself, but at the same time, it's not an equal sharing of electrons, so that's why we have a slightly negative charge for the oxygen and a slightly positive charge for the hydrogen. So, to recap, in a non-polar covalent bond, the two atoms have very similar electronegativities, so a very similar attraction for the electrons. It would be like a tug of war between identical twins. They both have the same strength. Let's say on a scale of 1 to 10, they're both about 5s. Well, the difference between their two strength numbers is very, very small. In fact, it's 0 in this case. So neither twin will be able to pull the electrons closer to itself than the other. So since their electrons stay in the middle, neither is going to be more negative and neither is going to be more positive. Instead, they'll end up as neutral and neutral. So that's what this symbol means. This triangle is actually the uppercase letter D in Greek. All right, so delta. So delta En is the difference in electronegativities. The difference between their electronegativities is just a small number, so small that neither atom is going to get the electrons more than the other, so they're going to equally share, resulting in a neutral-neutral charge. On the opposite end of the spectrum, we have one atom with such a high En value compared to another one with a very, very low En value, so that its attraction for electrons is so weak and its attraction for electrons so strong, it rips the electron permanently to this side over here. We call that an electron transfer. So that's similar to having a tug of war between an adult and a baby, also known as child abuse. Now in this case, the strength of the baby is probably like a 1, while the strength of the adult is probably a 10. So there's a huge difference in their strengths. Well, same thing. If there's a huge difference in their delta En values, then one atom is going to rip the electrons permanently to itself. Just like this one over here, the tug of war, it's not even fair at this point. The electrons will be permanently on this individual, leaving the baby with none. So it's lost its electron permanently, and now it's a positive charge. It's gained that electron permanently, and now has a negative charge. So when there's a large difference in electronegativities, large delta En, ionic bond. If there's a very small difference in electronegativities, small delta En, non-polar covalent bond. Now in the middle of these two extremes lies the polar covalent bond. It would be like a tug of war between a grade 8 student and a grade 6 student. Technically the grade 8 student should win, but every now and then you might find a grade 6 student who will get lucky and win the tug of war. So it's not a completely unfair fight like this one over here, and it's not a completely equal fight like this one over here. Instead, the electrons spend most of their time around the grade 8 students, but every now and then they'll go back to the grade 6 student over here. Well, same thing. The chlorine is not strong enough to permanently rip off the electron from the hydrogen, but the electrons will spend most of their time around the chlorine, and every now and then come back around the hydrogen, which leaves it with a partial charge. Not total positive, not total negative, but slightly positive, slightly negative. And this occurs when the delta En, the difference in electronegativity, is moderate. Not super high, not super low, but uneven. So now the question becomes, at what point does the delta En, the difference in their strengths, go from equal to unequal to unfair? So at what point does the delta En go from nonpolar covalent to polar covalent to ionic? Enter the delta En scale, or the electronegativity difference scale. Right? This scale goes from 0 to 4, and what we do is we subtract the En values for those two atoms and find out where they lie. If there's a very, very small difference between them, then it's nonpolar covalent. If there's a very large difference between their En values, then it's ionic, and if it's something in between, it's polar covalent. Now the important thing to keep in mind is that the electronegativity scale is a spectrum. It is not a scale with set defined borders. Yes, I put a number over here, but that's just there to give you a rough approximation. It's just a guideline, if you will. Take for instance this color spectrum over here. Where is yellow? If I asked where yellow is, most students would agree that this right over here is yellow. But if I asked where does yellow start? Now we're going to have a lot of differing opinions. Some students would go, oh, I'm starting to see some yellow here, while others will say, no, that's definitely orange. Others will say, I'm starting to see yellow here, but others will say, no, that's already past that point. It was definitely yellow before that. Well, similarly, I know where ionic is, right here. I know where nonpolar covalent is, right here. But at what point does nonpolar covalent turn into polar covalent? Somewhere around here. At what point does polar covalent turn into ionic? Somewhere around here. So we use these numbers as guidelines. If you look at different textbooks, you'll find different numbers. But in general, most textbooks agree 0 to 0.5 nonpolar covalent, 0.5 to 1.7 polar covalent, and 1.7 to 4.0 is ionic. But I prefer to think of these areas as gray areas. 0.4 to 0.6, that's when you'll start to see nonpolar covalent properties switching over to polar covalent properties. And 1.6 through 1.8 is where you'll start to see polar covalent turning into ionic. Now, I will never ask you, is this a polar covalent bond, or is it an ionic bond, or is it a nonpolar covalent bond? No, instead I'm going to ask you to compare between bonds. So I might say a CH bond versus an OH bond. Which one is more polar? Well, obviously the 1.4 has a higher delta En, so there's more polarity in this one than this one, which only has a 0.4 delta En. So instead of saying polar covalent and nonpolar covalent, over here you can just say it is weakly polar covalent. Similarly, in this borderline, you can have to say it's strongly polar covalent or weakly ionic. Alright, let's talk about dipole moments. A dipole moment is a vector quantity. Vector quantity means that it has both magnitude and direction, meaning it has both size and a direction. We can represent the dipole moment with an arrow like this. This arrow points in the direction of electron migration, so where are the electrons moving within this chemical bond? Since oxygen's En value is 3.5 while hydrogen is 2.1, the electrons are going to be dragged towards the oxygen. They're going to be attracted towards the oxygen. And that's what this dipole moment shows. It shows that the electrons are being dragged in this direction, in this chemical bond, and it leaves this side with a positive sign. That's why the dipole moment has this little positive tail, if you will. So as you can see, the dipole moment has a direction, but it also has magnitude. Take a look at the carbon-hydrogen versus the oxygen-hydrogen bond. Carbon has an En value of 2.5, while hydrogen has an En value of 2.1. To calculate the delta En, we take the 2.5, subtract the 2.1, and we get the 0.4. If you do the same thing for oxygen and hydrogen, its delta En is a 1.4. This bigger delta En shows that there's a greater charge separation. There's greater polarity. So polarity means to have opposite ends, north pole, south pole, for instance. In this case, the electrons spend most of their time orbiting around the oxygen because it's more electronegative, and every now and then they'll come back towards the hydrogen. Since they spend so much time around the oxygen, it's slightly negative, and since they don't spend as much time around the hydrogen, this end is left with a slightly positive. So that's our polar bond over here. All right, polar covalent bond, slightly negative pole, slightly positive pole, slightly negative end, slightly positive end. Meanwhile, with carbon and hydrogen, their delta En values are not super large. So its charge separation, its polarity, is less than that of the oxygen-hydrogen bond. Yes, the electrons will spend more time around the carbon than they would around the hydrogen, but it's not as big of a difference as if the oxygen was with the hydrogen. And so you'll still have that slight negative charge and slight positive charge here, but it won't be as great of a difference as with the OH bonds. So if you look back at the delta En scale, 0.4 is within that gray area where non-polar covalent is starting to switch over to polar covalent. So we would say that bond is weakly polar covalent. And we can represent these charge separations, this movement of electrons, with these dipole moments. So this arrow is much longer than this arrow over here because the electrons really get pulled towards the oxygen, while over here the electrons kind of get pulled towards the carbon. Alright, so dipole moments are vector quantities. They have direction, which way are they moving towards, and they have magnitude, how much of a charge separation is there. The greater the delta En value, the larger the charge separation, the more polar the bond is, the larger the dipole moment needs to be drawn. Now, a common mistake students make is mixing up the terms polar bond and polar molecule. They are not the same thing. Polar molecules are made up of polar bonds. Furthermore, just because the molecule contains polar covalent bonds doesn't mean the molecule itself is polar. I mean, if I put a stupid spoiler in my smart car and then enlarge the muffler exhaust so it's super loud and noisy, then stick on some racing badges, is my smart car a racing car now? No, it's not. Even if I put in a very powerful motor or engine inside the smart car, it still would not be a sports car. The aerodynamics of the car would not allow it to drive very fast. After about 130 kilometers per hour, the smart car aerodynamics become very, very unstable. It actually starts to flip over past that point. It's not enough to have the parts. There are other factors you have to consider. In this case, we have to worry about the molecule's geometry. Let's take a look at carbon dioxide, CO2. The En value for the carbon is a 2.5, while the oxygens are 3.5 for each of them. So when we calculate the delta En for each of these bonds, O and C, 3.5 minus 2.5, you get an En value of 1.0. Now 1.0 is well within the range of polar covalent, so that's not a problem. We'll draw the dipole moments for each bond. So for this bond, there's the dipole moment moving towards this oxygen. For this bond, the electron is going to move towards this oxygen, leaving this end slightly negative, this end slightly negative, and the carbon in the center slightly positive. So carbon dioxide has the parts. It has polar covalent bonds. But does the geometry allow for overall molecular polarity? To determine this, we're going to add up the vectors head to tail. So the head of one dipole moment added to the tail of the other dipole moment, and we'll see where the electrons go overall. Adding these vectors head to tail, we can see that they kind of cancel each other out. You go left, but then you go back right, and you end up at the exact same spot. In order for this molecule to be considered polar overall, it has to have opposite ends. One end would have to be partially positive, and the other end must be partially negative. But as you can see, neither side is more negative or more positive than the other. So in the end, this molecule's geometry, its shape, does not allow for polarity. It doesn't allow it to have opposite ends. As such, no net dipole moment. All right, there's no overall movement where the electrons are shoving to one side or over the other. All right, so CO2 is a non-polar molecule that contains polar bonds. Now, when you add up these vector quantities, it doesn't matter which one you add first. You can move to the left and then move back to your right. Or you can move to your right and move back to your left. In both cases, we started off in the same area and we end in the same area. So there is no net migration or net movement of electrons to one side over the other. All right, 1 plus 2 plus 3 is the same as 2 plus 3 plus 1. The order is irrelevant. Same thing. Adding up the orders does not make a difference. You'll get the same answer either way. Now let's think of water. H2O. 2 H's, 1 O. Oxygen's En value is 3.5. Hydrogen's En value is 2.1. So when we do a delta En calculation and subtract the two, their delta En values are 1.4. Again, 1.4 is well within the polar covalent range, so that's not a problem. So we'll draw in the dipole moments. The electrons will be attracted towards the oxygen because it has higher En value. So one dipole moment for this chemical bond and one dipole moment for this chemical bond. So please remember, you must draw a dipole moment for every chemical bond inside the molecule. Now when we add these dipole moments head to tail, so the head of the first dipole moment added to the tail of the next dipole moment, we see that there is an overall net migration or net dipole moment. The electrons overall seem to be moving up towards the oxygen end. So the electrons spend most of their time around the oxygen, making this end of the water molecule partially negative, and leaving this end, the hydrogen end of the water molecule, partially positive. Again, it doesn't matter if you added this dipole moment first, then this dipole moment, or if you added this one first and then this one. In both cases, they tell you the same thing. The electrons are migrating towards the oxygen end, migrating towards the oxygen end. Because the water molecule has oppositely charged ends, we can call this a polar molecule. It has polar covalent bonds inside of it, and its molecular geometry allows for polarity. It allows for charge separation. It separates the charges to opposite sides. Now, a common question students will ask is, why is water shaped like this while carbon dioxide is shaped like this? Couldn't you also draw carbon dioxide like this so that the dipole moments can add up and make it polar? The answer is no. But that's because carbon dioxide has a linear shape while water has a bent shape. In grade 12, you'll learn something called Vesper theory, valence shell electron pair repulsion. It essentially states that valence shell electron pairs will repel each other, and the shape of the molecule is the one that has the least amount of repulsion. Let's take a look at carbon dioxide. There are lone pair electrons on this side and lone pair electrons on this side. If I try to bend the carbon dioxide towards each other, these electron pairs, because they're negatively charged, would try to repel each other, because those like charges will repel. And if I tried to bend it the other way around, well, the same thing would happen, except these lone pair electrons would then try to push each other away because they're the same charge. So the best shape with the least amount of repulsion, where the electrons have the most amount of space, is a linear shape, a straight molecule. But when you look at water, there are two lone pair electrons at the top of the oxygen. And these electrons, same charge, will also want to repel. So if I tried to bring the hydrogens back up here and try to straighten them like I did with carbon dioxide, these lone pair electrons at the top would be too crowded and they would want to repel each other back down. And if I try to put these hydrogens too close together, their electrons will be too crowded and will repel back up. So the best shape for water with the least amount of repulsion, the least crowded amount of electrons, would be a bent shape, while the best shape for carbon dioxide with the least amount of repulsion, with the least amount of crowding of electrons, would be a linear shape. So students now ask, well, how do I know? How am I supposed to know that water is bent while carbon dioxide is linear? The answer is, well, you know now, because I've told you carbon dioxide is linear and water is bent. These two examples are fair game on a test. Alright, so on a test I will tell you if a molecule is going to be linear or bent, but you are responsible for knowing how to calculate the delta En values for each bond present in the molecule, and then determining whether there's going to be a dipole moment, and in which direction the dipole moments are moving, and then of course adding those dipole moments to tell me which direction are the electrons moving in overall for the entire molecule, or if they just end up canceling each other out, making a nonpolar molecule. Now, sadly, more complex molecules will require you to imagine these dipole moments in 3 dimensions. Alright, but for the purpose of this course, you are only required to qualitatively indicate whether a net dipole moment exists. Alright, so if you look at this 3D diagram, imagine if you were a diver and you had 4 dolphins pulling on you. One dolphin was pulling you towards the surface, one dolphin is pulling you towards the bottom of the ocean. Well, because they're pulling in opposite directions, these forces will cancel each other out. However, you have one dolphin pulling you into the page and another dolphin pulling you out of the page. Well, the in and the out components are going to cancel each other out, but overall these dolphins are pulling you forward. And so the net dipole over here, the electrons seem to be moving over here in this direction, leaving this end of the molecule partially positive and having all electrons end up on this side, making it partially negative. Alright, so as long as you can visualize where the electrons are migrating overall in these molecules, and these ones here, you should be good to go. Alright, so let's try out a question together. Is carbon tetrachloride, CCl4, a polar or nonpolar molecule? So the first step is to draw out the molecule itself. Carbon is in group 14 or 4a, so it's got 4 valence electrons. 1, 2, 3, 4. While chlorine is in group 17 or 7a, so it has 7 valence electrons. Over here. So it looks like carbon and chlorine will share 1 pair of electrons here. And since there are 4 chlorines altogether, I'll just draw them in a similar fashion as well. Now this is kind of messy, so I'm going to clean it up, and I'll get something like this. Now typically we only need to show the lone pair electrons for the central atom. The outer ones are not as important, so I've just kind of kept it out just to keep it a little clean and less cluttered. Next, we need to calculate the delta En for each bond that's present. I only see bonds between chlorine and carbon, so let's calculate that. Carbon has a 2.5, while chlorine has a 3.0. So 3 minus 2.5 gives me a 0.5, and that is in the weakly polar covalent range. So the dipole moment should be pretty small in size, and they're pointed towards the chlorines in each of these bonds. Now be careful, sometimes I'll see students doing delta En calculations for chlorine and chlorine, or if they really have no clue what they're doing, they'll just start subtracting random ENs for every single atom that they see and get like a negative 8.5. But obviously that is wrong. You only do delta En calculations for bonds that are present. So carbon, chlorine, bond. Carbon, chlorine, bond. Carbon, chlorine, bond. There's no such thing as a chlorine-chlorine bond in this specific molecule over here. They're not connected. So, since the electrons are moving towards the chlorines, each chlorine atom will have a slightly negative charge, not really big because it's weakly polar covalent, but a very slight negative charge, while the central carbon will be a slightly positive charge, I guess. We can now assemble these dipole moments, add them up head to tail, to see if overall are the electrons moving to one side of the molecule or the other. But it's clear at this point that the dipole moments cancel each other out, so wherever you started, you end up at the exact same location. These two dipole moments cancel each other out, and these two dipole moments cancel each other out. So there is no polarity to this molecule. There is no one end that's more negative than the other, and we refer to this molecule as being nonpolar. Now be careful, sometimes I will see on tests that students will write out that the molecule is nonpolar covalent. That's not correct. The word covalent is used when you're talking about the bond itself, not the overall molecule. So you just say the molecule is nonpolar overall. Don't write the word covalent. All right? The covalent word is used specifically when referring to the chemical bond itself. All right, so what I want to do is press pause, try out this question yourself. When you're ready, press play, and we'll take it up together. All right, so from the periodic table, we know that chlorine has 7 valence electrons, carbon has 4, and hydrogen has 1 valence electron. So I'm going to assemble them like this, and when I clean it up, it should look like this. When we do our delta En calculations, carbon has an En value of 2.5, hydrogen is 2.1, so their delta En is 0.4, which is in the weakly polar covalent range. Same thing with CCl, 2.5, 3.0 gives you 0.5. Now, it doesn't matter if you do 2.5 minus 3.0 or 3.0 minus 2.5, delta En is an absolute value, so it's always a positive value. It doesn't matter who you're subtracting first. In any case, the difference is 0.5, which is also in the weakly polar covalent range. We can then draw on our dipole moments. With the CH bond, the electrons are moving towards the carbon because it's more electronegative, but not by much, but it's going to move in towards the carbon. While over here, the electrons are moving towards the chlorine in each of these bonds. Once again, be careful. Sometimes I'll see students drawing delta En calculations for H and Cl, but H and Cl aren't even connected to each other, so you can't do a delta En calculation if there is no such bond. I'm going to add up my dipole moments now. Again, it doesn't matter where you start off with first, so I'll just start from the top. We're going to go down, then we're going to go to the right, then we're going to go down again, then we're going to go to the left. And so overall, the electrons seem to be migrating towards the bottom of the molecule over here, making this end of the molecule slightly negative and leaving this end of the molecule slightly positive. But keep in mind that these are only weakly polar covalent bonds, and so these dipole moments are pretty small, making this a weakly polar molecule overall. Alright, so our next video will be on drawing line diagrams.